Okay, I'm recording. Okay, so we applied the 6-step procedure called Gauss-Jordan elimination to get an arbitrary matrix to reduce for echelon form. Okay, and the goal is to say that the linear system corresponding to this matrix has the same solutions as the linear system corresponding to this one. And why we get it to reduce row echelon form is that we have a simpler matrix. Okay, but a matrix in reduced row echelon form is in a simpler way, in such a way that when we look at the corresponding linear system, we get its solutions. Okay. Now we either get the solutions because it's obvious, like x1 equals 1, x2 equals 2, x3 equals 3, x4 equals 0, something like that, because we have a unique solution. Or if there are infinitely many solutions, instead what we get are parametric equations. Okay, we have leading variables which correspond with leading ones, and then we have free variables corresponding with variables that do not have leading ones. Okay, so we have free variables which are represented by parameters, and we have leading variables. Okay, but in any case, what we're doing now is we're taking matrices, arbitrary matrices, and we're getting them to what's called reduced row echelon form. Okay, and that procedure is called Gauss-Jordan elimination. Okay, so you need to, the end notes here are on the whiteboard here. Okay, I wrote them here because it's next to these matrices. Okay, so today we want to do another example of Gauss-Jordan elimination. Okay, so last class we did Gauss-Jordan elimination to take a particular matrix to reduced row echelon form. And so I also defined Gauss-Jordan, Gauss-Jordan elimination. Okay, it's the 6-step procedure that we did last class to do that example. Okay, so now we're going to, this class, we're going to just continue. So the first thing we're going to do is example 5. And so example 5 is an example of Gauss-Jordan elimination. And so the example is solved by Gauss-Jordan elimination. And so here's the system. It's x1 plus 3x2 minus 2x3 plus 2x5 is equal to 0. The second equation is 2x1 plus 6x2 minus 5x3 minus 2x4 plus 4x5 minus 3x6 is equal to -1. The next equation is 5x3 plus 10x4 plus 15x6 is equal to 5. And 2x1 plus 6x2 plus 8x4 plus 4x5 plus 18x6 is equal to 6. This is our linear system. I'm just going to try to line this up. Actually, I'll just line it up this way. Okay, so this is our linear system. So I'm doing is just lining everything up. So you want the x's, the coefficients, the x1s, the x2s, the x3s, the x4s, the x5s, x6s, the equal signs, the numbers, coefficients. You want things to line up. And so when you're writing it down by hand, this is easier to do. Okay, so this is our linear system. And so okay, so this is the linear system that I wrote down. So the question Sabrina is asking is, so you put the 0 on the empty spots when doing reduced echelon form. Well, so when you're talking about reduced echelon form, you're talking about the matrices, right? You're not talking about the original linear system. So here I'm writing out the linear system, right? When you're talking about the matrix, you can't have the entries have a number in them, right? So you would have a 0, right? But when you're writing out the linear system here, right, with the variables and all of that, this is not a matrix, right? When you're writing out the system, you don't need to write plus 0x4 plus 0x6, right? If there's none of a certain variable, you don't have to write it at all, right? Right? Like if you were to have x equals 1, you wouldn't have to write x plus 0y equals 1. Or you wouldn't have to write 1x plus 0y equals 1. You would just leave out the variables if there's 0 of them. That's if you're writing out the equations, right? You don't have to include the variables if there are none of them. If you're writing the matrix, though, any matrix, you can't put a blank in an entry if it corresponds with an amount 0. So you would put the number 0 in the matrix, okay? So for matrices, you put the number 0. For equations, if you have none of a variable, you just leave it out. Okay, so this is solved by, you're welcome. So this is solved by Gauss-Jordan elimination. So what we want to do is we want to take this linear system, we want to look at its corresponding augmented matrix. Okay, so what I'm going to do is I'm going to do that on the whiteboard. Okay, so we have that linear system. We are now going to look at the augmented matrix corresponding to that linear system. And maybe, though I don't want to do this, I might rewrite the linear system I just typed down. I'm going to write it here. Okay, I'm going to write by hand. Okay, so x1 plus 3x2 minus 2x3 plus 2x5 is equal to 0. The other one is 2x1 plus 6x2 minus 5x3 minus 2x4 plus 4x5 minus 3x6 is equal to -1. 5x3 plus 10x4 plus 15x6 is equal to 5. 2x1 plus 6x2 plus 8x4 plus 4x5 plus 18x6 is equal to 6. Okay, so this is the linear system. Okay, so we just want the corresponding augmented matrix for this linear system. The corresponding augmented matrix is just 1, 3, -2, 0, 2, 0, and then there's a 0 here. You have 2, 6, -5, -2, 4, -3, -1, 0, 0, 5, 10, 0, 15, 5, 2, 6, 0, 8, 4, 18, 6. Okay, so this is the corresponding augmented matrix for that linear system. You just put the coefficients here. Sometimes people put a vertical line here. I do that. That way you separate the coefficients of the x's here and the constants at the end of the equation here. Okay, so this is our corresponding augmented matrix. And so now we're going to get this to reduced echelon form. And so to do that, we are going to perform elementary row operations on matrices to get simpler ones. to get it to eventually to reduce row echelon form. But we're going to use the Gauss-Jordan elimination to do it. So first we're going to add -2 times the first row to the second. So we're going to add -2 times the first row to the second row and also to the fourth row. Okay. So remember the steps of Gauss-Jordan elimination. Let me maybe go to lesson or previous whiteboard. This is from last class. Step 1 was locate the leftmost column that does not consist entirely of zeros. Step 2 was interchange the top row with another row if necessary to bring a non-zero entry to the top of that column found in step 1. Step 3 was if the entry that is now at the top of the column found in step 1 is A, multiply the first row by 1 over A to introduce a leading 1. So here you multiply this row by 1/2. Now there's a 1 here. Okay, add suitable multiples of the top row to the rows below so that all entries below the leading 1 become 0. So in this case, you would add -2 times the first row to the third. So that way that you would end up with a 0 here. So at the end of step 4, you've located the leftmost non-zero column. You've made the top entry a 1 and everything else below it is 0. So that were the first 4 steps. Step 5 is now cover the top row of the matrix and begin with step 1, apply to the submatrix that remains. So if you cover up the top row, which has this 1 on it, the submatrix is the thing I have in orange brackets here. This is the submatrix, and you start again at step 1, meaning you locate the leftmost non-zero column in the submatrix. I use orange here now to the thing I removed. The leftmost non-zero column in the submatrix, you make the topmost entry a 1. You then make the entries below it a 0. You've now finished the 4 steps again. You cover the top row and you continue. Now, when you cover the top row, you locate the leftmost non-zero entry. You multiply that row by 1 over that entry. So 1 over 1/2, you multiply it by 2. And so now you locate the leftmost non-zero column in now the new submatrix. You have the topmost entry as a 1, and all the entries below it are 0 because there are no other entries. It's true vacuously. And so now you look at this matrix and it's in row echelon form. And so when it's at the end of step 4, if your matrix is now in row echelon form, you don't go back to step 1. You move on to step 5. That is step 5. Step 5 is if your matrix is now in row echelon form. After step 4, you move on to step 6. If it's not in row echelon form, you go back to step 1 and repeat. Okay, but it's in row echelon form. We end step 5, we move to step 6. In step 6, you start with the bottom row. You locate the leading 1 in that row. You then look at the column it's in. You look above it, and you get all the entries above it to be 0. So in the bottom row, the leading 1 is here. You locate the column it's in. You make all the entries above it 0 by adding suitable multiples of this blue row to the rows above it. So that way you change these entries from non-zero numbers to 0 numbers. Now you have everything else above it as 0. You then proceed upward. You then move to the next column, next row. And you say, okay, what's the leading 1 in this row? It's this thing in green. You say, okay, the entries above it will have to be 0. So in this case, you'd add 5 times the brown row to the top row, and then you get this entry to be 0. So now you're done with this row. And then you'd move on to the top row, but the leading 1 is here. And you also can tell that now this entire matrix is in reduced row echelon form. So in step 6, you keep going from the top row up to another row until the matrix is in reduced row echelon form. So now here it is. And then the 6-step procedure is done, and you've got your original matrix to reduce row echelon form using these 6 steps. Okay, so that one kind of fast, but what's happening here? So what's happening here is we have this matrix, and so if you locate the leftmost non-zero column, it's this, and what you want is the top entry of that column. I want to check to make sure I'm using the colors the same as I did last time. So it was blue, and then the top one was green. So then you locate the top. You locate the top entry and I'm going to make it green. So you locate the top entry, and that's there. Now, if it's not a 1, you multiply it by 1 over the value that entry, and then you get it to be a 1. It's already a 1, and so now that's already a 1. You don't have to get it to be a 1. Now add suitable multiples of this row to the correct bottom row so that all the entries below it are 0. So the entries that are non-zero are this 2 and this 2. And so, okay, so so here, did I? Right, okay, so here in red, I put the ones that were non-zero below. So I'm going to do that here. So here, the problem is this entry and this entry. So these two entries are non-zero, and so that's a problem. And so we want them to become 0. So what do you have to do? You have to multiply the first row by -2 and you have to add -2 times the first row to the second, and you have to add -2 times the first row to the fourth. And that's what we're going to do here. We're adding -2 times the first row to the second row and also to the fourth row. Okay, and then that would result in all the entries below this one being 0, or changing these 2's to 0s via elementary row operations only. So this, yeah, it's a very long procedure. Okay, so now let's keep going. So we have this matrix and we want to get it to reduced echelon form. So what I'm going to write now is the result of taking -2 times this row, adding it to this one, and -2 times this row and adding it to that one. Okay, and so this is what you get. So you have 1, 3, -2, 0, 2, 0, and then this is the coefficient at the end. You have 0, 0, -1, -2, 0, -3, -1. You have 0, 0, 5, 10, 0, 15, 5, 0, 0, 4, 8, 0, 18, 6. Okay, so you do need to do examples and you need to be able to do these calculations, but they're just addition, multiplication, subtraction, stuff like that. Okay, what's happening here is I took -2 times this row and add to this one. When I do that, -2 times 1 is -2. -2 plus 2 is 0. Here, I'm going to say the number happens. -6 plus 6 is 0. 4 plus -5 is -1. 0 plus -2 is -2. -4 plus 4 is 0. 0 plus -3 is -3. 0 plus -1 is -1. And so we get these values here. And so the third row stays the same because we're not doing anything to the third row. And then we add -2 times the first row to the fourth, and we get 0, 0, 4, 8, 0, 18, 6. Okay, so you do those operations and you get this. If the calculations, if you're not following me doing the calculations because it's fast, the main concern is not really the calculations themselves. I'm hoping you don't have a problem with addition, subtraction, multiplication, division. It's about knowing what steps to do and understanding how they're executed. The calculations themselves you can do while you're studying. If you want to review the calculations, those are things that are easy to see while you're studying on your own. What I want to impress upon are the steps I'm doing more than the calculations themselves. Okay. Okay, so now our leftmost column that we identified before is this one. And the topmost entry of that column is a 1, and all the entries below it are 0. And so these are the first 4 steps. And so we get to the 5th step, and the 5th step says cover the topmost row and think of the rest of it as the submatrix. And so now we only work with the submatrix. And so now since this matrix is not it's not in row echelon form because not every row has a leading 1. There's 3 properties, but one of the properties fails because it doesn't have a leading 1 every row. In the second row here, there's the first non-zero value is a -1. And in order for it to be it has to have a leading 1 at the start, right? So every non-zero has to have a leading 1, but it doesn't. So we know this entire matrix is not in row echelon form. And so when we get to step 5, instead of moving on to step 6, we cover the topmost row and we revert back to step one. Okay, so we revert back to step one. And so in the submatrix now, we've covered up the orange thing, and we're looking at the submatrix, and we're looking at the leftmost non-zero column in the submatrix, right? Before, this was the leftmost column because we were looking at the entire matrix, and there was a 1 here, right? So this was a non-zero column. When we cover the top row and go back to the first step, we now don't care about this top row. And so this is a submatrix, the leftmost non-zero column. This is not a zero. This is not a non-zero column because we're covering the 3, right? We're covering the entire top row, which means that this column is only zeros and this column is only zeros now without that first row. So leftmost non-zero column is this one. We identified the top entry. This is the top entry in that leftmost column of the submatrix. And that topmost entry has to be 1. And so in order to get to be a 1, we multiply the row it's in by -1 so that we have a 1 there. Okay, so what we do is we multiply the top row of the submatrix, right? We're living in the submatrix now. So multiply the top row of the submatrix by -1 to get a 1 at the top of the column chosen. Okay, so that's why we are multiplying by -1, so that the top entry of that selected column is now a 1. Okay, so we do that, and so we still have 1, 3, -2, 0, 2, 0, 0. We're multiplying by -1, so this is 1, 2, 0, 3, 1. And then everything else stays the same. 0, 0, 5, 10, 0, 15, 5. And 0, 0, 4, 8, 0, 18, 6. Okay, so the top row, this is still the top row that we removed. This was the original leftmost column. Okay, but now this is the new leftmost column. This was the top entry of that leftmost column, which is 1, 1, everything below. Now this new one has this as the top entry after we multiply this row by -1, right? So now we have the top entry as a 1. And so now what we need to do is make all the entries below it 0 by adding suitable multiples of that row. So what we need to do is we need to add -5 times this row to make this a 0. And we need to add -4 times that row to this row to make this a 0. Because these two entries are non-zero. We need them to become 0. So -5 times this row plus 0, -4 times this row plus that is 0. Okay, and so then all the entries below it will be 0. And so below this in text, I'm going to type in this next step. So we're now going to add -4 times the top row. By the top row, I mean of the submatrix, right? So the row that exists in this top row removed is no longer, we're not thinking about. So top row means this row. Okay, so add -4 times the top row to the second row, right? Again, there's no this row. So second row means the second row of the submatrix. So it's this row. So add -4 times the top row to the second row, and not -4, -5. Add -5 times the top row to the second row, and add -4 times the top row to the third row. Okay. Okay, and so then that way we will then get these entries to be 0. So in the next page, I'm going to take the result of adding -4 times this row to this one to make this a 0. I mean, adding -5 times this row to this one to make this a 0, and adding -4 times this row to this row to make this a 0. Okay, so I'm going to write that down here. Okay. Okay, so here's the matrix. Our top row is unchanged by this operation, so it's still 1, 3, -2, 0, 2, 0, 0. The next row is 0, 0, 1, 2, 0, 3, 1. Now, the result of that next operation will make everything in this row 0. And also we'll get this. Okay, so we still have the top row removed. Okay, we still have to have it there. We still have to know it's there because at the end we'll need it. But just right now we're not using it. And this is now that entry at the top of that one. The leftmost column, right, of the submatrix was this. The top entry was this. And now all the entries below it are 0. Okay, now that all the entries are 0, we can now go to step 5. And step 5 says if your matrix is in row echelon form, you can move on to step 6, right? But if we look at this matrix, there's 2 reasons. There's 2 automatic reasons I see it's not in row echelon form. One, the third row is a 0 row, but for a matrix to be in row echelon form, all the zeros have to be grouped at the bottom, and this one isn't. So it fails to be in row echelon form. Also, this row is a non-zero row, but it doesn't have a leading 1. The first non-zero entry is not a 1, and so it does not have a leading 1. And so there's 2 reasons right there for why this matrix is not in row echelon form. Okay, so this matrix is not in row echelon form, which means we go back to step 1. Okay, and so when we go back to step 1, we look at the leftmost non-zero column of, since this is not in row echelon form, we cover the topmost entry, topmost row of what now our submatrix, and we go back to step 1 and we repeat the procedure now. That's because this entire matrix is not in row echelon form when we get to step 5. Okay, so now that it's not in row echelon form, when we get to step 5, we go down the track, and we cover the topmost row of the submatrix we're in, and we go back to step 1. Step 1 is locate the leftmost non-zero column. This is the leftmost non-zero column. Okay, even though the top entry is a 0, the column, this column as a whole, does not consist entirely of zeros. All 5 of these first columns in the submatrix are only zeros, and so this is the leftmost non-zero column, a column in which at least one of the entries somewhere in the column is non-zero. Okay, so next, what we want is the top entry to be non-zero. The top entry is 0. So what we need to do is we need to switch rows appropriately so that we get a non-zero value there. We're only living in the submatrix, so we do that. So there's the obvious way to do that. We just switch this row and this row, right? If we switch these 2 rows, then the 6 will be here and the 0 will be here. So we'll have a non-zero entry at the top. Okay, so let's do that. Okay, so switch rows 1 and 2 to get a non-zero value at the top of the column chosen. Okay, the column we chose is the leftmost non-zero column in the submatrix, right? And rows, this is now row 1 in the submatrix to live in, and this is now row 2. So we're going to switch those 2 rows and have now a non-zero quantity at the top of that row. Okay, so the entries everywhere else are the same: 1, 3, -2, 0, 2, 0, 0. We also have 0, 0, 1, 2, 0, 3, 1. And then so now we switch the 2 rows. So now we get 0, 0, 0, 0, 0, 6, 2, and then 0, 0, 0, 0, 0, 0, 0. Okay, so we already covered these 2 rows, and so I'm gonna redraw on these columns just to enforce these ideas. That was the first leftmost non-zero column called. The topmost entry was there. This column, which we dealt with before, and then that was the topmost entry. Now we have, this is the new leftmost non-zero column. What we did was we changed the topmost entry. Instead of being 0, it's now a non-zero value. Okay, so now that we have that, our next step is going to be to just multiply the top row by 1/6. So that way, instead of having 6 here, it's a 1. And so what we want is a leading 1 at the top of this non-zero column. Okay, so I'm going to write that in text right here. So next, we multiply the top row by 1/6 to have a leading 1 in the row, or have a 1 at the top of the column we chose. Okay. Okay, so we want a 1 here in this green spot. So we just multiply the row it's in by 1/6. So that way it becomes a 1. So the next page, I'm going to write the result of that. Okay, so I think you're probably starting to see why I'm doing all these steps, or maybe just how they're being done, and you're kind of seeing you're seeing why I might have this procedure done in this way, right? You're seeing how the matrix evolves, or how this matrix is going to get simpler. You might even believe that it's going to get to reduced echelon form. See how we're getting there. These steps, how these steps would definitely get us to row echelon form and reduced row echelon form. So I multiplied by 1/6, and so now it's that. And the 0 row is here. These are all zeros, and so they're still all zeros. Nothing changed there. So the topmost row, we covered this row already, and we covered this row already. Again, this was the leftmost column, where the top entry was a 1 in that previous step. There was another leftmost non-zero column here earlier, and this was the non-zero one at the top of that one. Here's our current leftmost non-zero column in the repetition steps now, and the top entry is now a 1. Okay, so now we have the leftmost non-zero column. The top entry was non-zero. Now it's also non-zero. It's also a 1. We need to make all the entries below it 0. It already is. And so since it already is, we're done with step 4. We go to step 5. And now that we're in step 5, we ask ourselves, there's 2 tracks we can go when we get to step 5. Either the matrix is in row echelon form, it is in row echelon form, and we move on to step 6, or it's not in row echelon form. We cover the top row, and then we go back to step 1 and repeat again. Well, this matrix is now in row echelon form. Every non-zero row has a leading 1, non-zero row leading 1, non-zero row leading 1, non-zero row leading 1. That's a 0 row, doesn't matter. All the 0 rows are grouped at the bottom. This is a 0 row and it's grouped at the bottom. There are no other 0 rows. Third, every 2 consecutive rows that are non-zero, the leading one in the lower one is further to the right than the leading one above it. So this leading one is further to the right than this one, and this leading one is further to the right than that one. And this is a 0 row, so there are no other consecutive non-zero rows. There's only 2 pairs of consecutive non-zero rows, the first and the second, and the second and the third. In both cases, the lower one is further to the right than the one above it. That one's further right than this one's further right than that one. So this matrix also satisfies property 3. And so a matrix being in row echelon form are those 3 properties. Every non-zero row is leading 1, all the 0 rows are grouped at the bottom, and every 2 consecutive non-zero rows, the leading one and the lower one is further to the right than the leading one in the higher one. Okay, so those are the 3 properties for a matrix in row echelon form, and this matrix satisfies those 3 properties. So this matrix is in row echelon form. Okay, that was a little fast. But the point is, this matrix is in row echelon form. That means that we move on. That means that step 5 tells us to move on to step 6 in this instance. Okay, so move on to step 6. So in step 6, we already have the matrix in row echelon form. The goal of step 6 is to get our matrix from row echelon form to reduced row echelon form. Okay, and so where steps 1 through 5 was starting at the top and moving down, step 6 is starting from the bottom and moving up. So we start at the bottom and we work our way up. The bottommost row, maybe I can think of a color that really brown. Okay, so then you start with the bottommost row and you take the leading 1 in that row and you add suitable multiples of it. So that way you get all zeros above. There are no leading 1s in that bottommost row. I don't want to choose that color now. I'm going to choose pink, purple, or this color, pink. Pink, yeah. So there's no leading 1s here. So we keep going. So now that we go to the next row, which is now this one. And this row, we take the leading 1 in this row, which is here, and we add suitable multiples of it to the ones above it so that all the entries above it are 0. And so the entries above it, let's go with Let's go with purple. So here we have this here. So moving up the second to bottom row, repeating this procedure, we have leading one here. We want to make all the entries above it 0. So we have a 3 here. So here the 3 is the problem. We want that to be a 0. So we take -3 times this row and we add to this row. So that way -3 times 1 is -3 plus 3 is 0, and that becomes a 0. And so all the entries above this leading one become 0. Okay, before it was all the zeros below, now it's the ones above. So we have this 1, -3 times this row, this one, and we get a 0. Okay. In applying step 6, we first need to add -3 times the third row to the second. Okay. And then that will make a 0 where that -3 is. So let me rewrite this matrix here. Hopefully there's enough room. So we have 1, 3, -2, 0, 2, 0, 0, 0, 0, 1, 2, 0. Oh, so -3. Yeah, okay, good. That's fine. And it's a 0. And then adding, these are all 0. So adding -3 times them is also 0. So adding that amount, which is 0 to these, doesn't change it. -3 times 1 is -3. -3 plus 3 is 0. -3 times 1/3 is -1. -1 plus 1 is 0. And you have a 0 there. This row stays the same. And the bottommost row are all zeros. Okay. Oh, okay. We're not blocking rows anymore. So what's happening now in step 6 is that, right, we started with the bottommost row and there was nothing to do. We have the next row here and the leading one, which I'm still going to have as green because that matters. And then we looked at the column containing that one and above it. And now we have all zeros in that column, right? And so now we move on to the next row up for step 6. This is step 6. And so we go to the next row. Once we locate a leading one in a row and we make all the entries above it in that column 0, we then select the next row. And then we go up to the next row and do the same thing where we select the leading one in that row. And we say, okay, I want to make all the entries above that leading one in the column it's in. I want to make all those entries 0. So the problem is this entry, because this entry is not 0. So we need to add 2 times this row that I selected to this one. So that way that entry becomes 0. Okay, so I'm going to do that and you'll see that they'll result in a 0 at this spot. Okay, so now let's go here. Okay, so starting at the bottom, 1, 2, 6, 1, 2, 3, 4, 5, 6, and a 0. Then we have 5 zeros, 1, 2, 3, 4, 5, and a 1, and then 1/3. And then next we have a 0, 0, 1, 2, and then 0, 0, 0. And then the top row is 1, 3, 0. 1, 3, 0. I don't know if you can see the whiteboard, right? Okay, so 1, 3, 0, 4, 2, 0, 0. So now we have this matrix. This is the top bracket there. Okay, so now, right, this was the first row we selected. Then we moved up to this row. And when we got to this row, we had this non-zero, and we had this leading one in this row. We then located the column it was in above it, got them all to be 0. When that happened, we then moved up to the next row here. This is all step 6. Then we located the leading one in this row. Then we looked at the column it was in above it, at and above it, and we made this entry now a 0. Before it was non-zero, now it's a 0. And so now we've succeeded at taking the leading one in this row we selected, making all the entries above it 0. Then we can move up to the next row. And the goal is just you locate the leading one in that row, you make all the entries above it 0, but there's nothing above it, and so we're automatically done. So now we're done with step 6. Okay. Okay. We are now done with step 6 because all of the leading ones have zeros, have only zeros above it. Okay, so that was the goal of step 6. We located every leading one and we made sure there were only zeros above it. If there weren't, we add suitable multiples of the row with the leading one to the rows above it, so that way we would get zeros to be there. Okay, so we are succeeded at making only zeros above every leading one. And since we finished step 6 and of this procedure, the procedure tells us we now have a matrix in reduced echelon form. And if you check it, it is. Now that we are done with step 6 of Gauss-Jordan elimination, our matrix is in reduced row echelon form. Okay, so our matrix is in reduced row echelon form. Okay, so we are now done with Gauss-Jordan elimination. So now what I'm going to do is I'm just going to write out the corresponding linear system. Okay, so the corresponding linear system is the following. We have x1 plus 3x2 plus 4x3 plus 4x4 plus 2x5 is equal to 0. X3 plus 2x4 is equal to 0. And we also have x6 equal to 1/3. And we also have 0 equals 0. I'm just going to write that in so that it's complete. Okay, the last row corresponds with 0 equals 0 because there's 0 of each variable and you add them together. That means it's 0 and that's equal to 0. Okay, so this is the corresponding linear system to that augmented matrix. The third equation you can leave out, right? You don't need it because saying 0 equals 0 doesn't add or doesn't change the solution set of the linear system. And so if we just got rid of that equation, the solution set would stay the same. Okay. And so what we want essentially are we have our system. Once we get our matrix in reduced echelon form, the corresponding linear system is simplified so that we can get the solutions from it. Okay, there's clearly not exactly one solution. All right, it's not a simple x1 equals 1, x2 equals 2, x3 equals 0, and so forth. We have infinitely many solutions. And so to get all the solutions, we need to look at the parametric equations that we would get from this system. Okay, so let's first look at the leading ones here in our matrix in reduced echelon form. These leading ones correspond with the following variables. This x1 corresponds with that leading one. This x3 corresponds with that x1. I'm just going to write the green circle bigger so that way it doesn't cover it up. This x3 corresponds with that leading one. And then x6 corresponds with this leading one. So we have 3 leading ones that are circled in green, and that corresponds with these 3 variables, x1, x3, and x6, which I also circled in green. These 3 are our leading variables. Okay, those 3 are our leading variables. Okay, but now we also have other variables, and those variables are called free variables. Any variable that is not a leading variable is called a free variable. And so these free variables I'm going to denote by orange. Okay, so x2, there's 3x2. We're not ignoring the coefficient, but I'm just pointing out the variables. x2 is a free variable, x4 is a free variable, and x5 is a free variable. So these are the free variables. Any variable that is not a leading variable. So first you find all the leading variables, and every other variable is a free variable. Okay, so x2, x4, and x5 are free variables. And so what you do when you have free variables, you set each of them to its own parameter. Okay, and so let's set, we're going to set x2, which is a free variable, equal to r. We're going to set x4, which is another free variable, equaling to s. And we have another free variable, which is x5, which is equal to t. So you have rst. And so those correspond with the variables x2, x4, and x5. And so now we've assigned every free variable its own distinct parameter. And so what you do is your parametric equations are, well, each free variable equals its corresponding parameter. So x2 equals r, x4 equals s, and x5 equals t. And then for each leading variable, we solve for it in terms of the free variables. And then we substitute the free variables for the parameters we assign to them. So if you'll notice, x1, the only other variables other than x1 in this equation are free variables. x2, x4, and x5 are free variables. x3, which is a leading variable, the only other variable in its equation is a free variable, x4. And x6 doesn't have any other variables in it. And so whenever you have your matrix in reduced echelon form and you look at its corresponding linear system, the linear system will have leading variables and free variables. But the equations that the leading variables lay in, all the other variables are free variables. And so because we now have a linear system of this form, we can solve for each leading variable in terms of only free variables. And since you're substituting each of those free variables with its own parameters, you can actually solve for each leading variable in terms of only these parameters. Okay, so x1 is going to equal -3r minus 4s minus 2t. x3 is going to equal -2s, and x6 is going to equal 1/3. Okay, and so what we will then have each leading variable in terms of those same parameters r, s, and t. Okay, I chose r, s, and t because they're in alphabetical order. Okay, so usually t is used, and then if you have 2, it's st, and if it's 3, it's rst. Okay, so that way t is one of them, and then they're in order. So x2 is r, x4 is s, x5 is t. As the indices go up, you can move forward in the alphabet, rst. Okay, so then what I'm going to do is I'm going to solve each leading variable in terms of its free variables. Okay, so next I solve each leading variable in terms of only free variables. Okay, so when we do that, we have x1 is equal to -3x2 minus 4x4, and then minus 2x5. We have x3 is equal to -2x4, and then we have x6 is equal to 1/3. Okay. We already have that x2. We already signed x2 to r, x3 to s, not x3, free variables. So x4 equals s, and then x5 is equal to t. Right, those are our assigned parameters to each free variable. Right, these are the free variables are the leading variables are in green, and then the free variables are orange. So these are the leading variables from earlier. These are the free variables from earlier. And so we have each of the leading variables in terms of only free variables. Those three are each free variables. This is a free variable, and there are no variables here. And so it's only in free variables factors that are not. Okay, so or just it's only okay. So now we have that, and so lastly, we substitute the free variables for the corresponding assigned parameters. Okay, and so when we do that, x1 is equal to -3 x2, which is r, minus 4 x4, which is s, and then minus 2 x5, which is t. x2 is equal to r. x3 is equal to -2 x4, which is s, and x4 is equal to s, and x5 is equal to t, and x6 is equal to 1/3. So I don't think I'm going to put a vertical line. I don't want to. Well, it's all 6, so I'm using the vertical line just so that you don't confuse this equation. It's not part of that equation, right? So these 6 equations are the parametric equations that describe the entire solution set of the original linear system. Okay, so I'm going to write that down. So you have this, so that we're now done with that. I'm just going to explain in words here what that represents. What I just said. We now have from the previous slide the parametric equations that describe all the solutions of the original linear system. For each assignment of real numbers to each parameter, we have corresponding values of the variables that solve the entire original linear system. Okay, so we now have from the previous slide the parametric. We now have from the previous slide the parametric equations that describe all the solutions of the original linear system. For each assignment of real numbers to each parameter, we have corresponding values of the variables that solve the entire original linear system. So here we have x1, x2, x3, x4, x5, x6, right? These are parametric equations. The parameters are r, s, and t assigned to x2, x4, x5. But if we assign any real values to those 3 parameters, let's say r is 1, s is 2, and t is 3, then correspondingly we'll have values for x1, x2, x3, x4, x5, and x6. Those values we can plug in to our original system, this original system. And the first thing will equal 0. The second thing will equal -1. The third expression will equal 5. And the fourth expression will equal 6. Okay, and that'll be for that assignment of values. If instead we let r equal 100, s equal 200, and t equal 300, we then have another corresponding values for all 6 of these variables. And those 6 variables with those corresponding values would satisfy this entire linear system. It would satisfy all 4 equations. All 4 equations would be true. Okay? And so you have infinitely many ways to choose values for r, s, and t. And so for each of those infinitely many ways, you have a corresponding values of these 6 variables, which correspondingly solve this entire linear system, solve all 4 of the equations in it. Okay? And so we now have a representation by these parametric equations, a representation of all the solutions, every single one of the original linear system. Okay, any questions about this? Okay, good. Okay, so we are now done solving that system via Gauss-Jordan elimination. Okay, so on the whiteboard, we found a corresponding augmented matrix and got it to reduced row echelon form. You can see word, right? Okay. So on the whiteboard, we found a corresponding augmented matrix to this linear system and got to reduced row echelon form. Then we wrote down the corresponding linear system to that augmented matrix in reduced row echelon form. That linear system, then we found the parametric equations that represented all the solutions of the linear system. Okay, so that was example 5. And so we did that on the whiteboard. So now we're going to talk about homogeneous linear systems. Okay, so homogeneous linear systems are just linear systems where the constants on the right-hand side are all 0. So I'm going to write that down. Definition. A system of linear equations is said to be homogeneous if the constant terms are all 0. That is, the system has the form as the following form. A11 x1 plus A12 x2 plus ... plus A1n xn is equal to 0. So that's the first equation. The next one is A21 x1 plus A22 x2 plus ... plus A2n xn is equal to 0. Okay, and then you continue, and so it's ... And the last row is A. So there are m rows. This is AM1 x1 plus AM2 x2 plus ... plus AMN xn is equal to 0. Okay, and so you have this linear system, right? So remember, we went over the general form of a linear system, but we had constants b1, b2 to bm on the right-hand side. A linear system that's called homogeneous is one in which all the b's on the right-hand side are 0. And so we have zeros on the right-hand side. The left-hand side is the same as a regular linear system would be. It's just that for homogeneous, we're adding an additional structure that the right-hand side is all the constants on the right-hand side are 0. Okay, every homogeneous system of linear equations is consistent because all such systems have the solution where all the variables are 0. So have x1 equals 0. I'm going to put enter here. Have x1 equals 0, comma, x2 equals 0, comma, ... comma, xn equals 0 as a solution. Okay, right? So if all the right-hand side values are 0, then if you make every variable 0, all the left-hand sides will be 0, and every equation will be true because every equation will be 0 equals 0. And so a linear system being consistent means it has at least one solution, right? And so every linear system every homogeneous linear system is consistent because it will always have a solution, specifically the solution where all the variables are assigned the value of 0. Okay, so this solution where all the variables are assigned the value of 0, this solution is called the trivial solution. Okay, the trivial solution is when all the variables are assigned the value of 0. It's not every linear system has a trivial solution, but So every homogeneous system has the trivial solution. Okay. If there are other solutions, they are called non-trivial solutions. Okay. So any solution that is not assigning every single variable to 0 is called a non-trivial solution. Okay, so because a homogeneous linear system always has the trivial solution, always has a trivial solution. There are only two possibilities for its solution. So remember earlier I said there's three possibilities: either 0 solutions, exactly one solution, or infinitely many solutions for a linear system. You can only have 0, exactly 1, or infinitely many. You cannot have 2 solutions to a linear system. And that had to do with looking geometrically at the representations of the linear system as either lines or planes. There's a more abstract proof, but we're looking at it in 3-dimensional space. And it's the intersection of these geometric objects. And so when you intersect all these geometric objects, they can either have no intersection at all, 0 solutions. You have exactly one solution, they all meet at exactly one point. Or the only other way to intersect, if they don't intersect at a single point, they would have to intersect at infinitely many points. And so those infinitely many points in intersection correspond with infinitely many solutions. So you can't have 2 lines intersect with 2 points, right? Two lines are straight, right? In the example of 2 space, every linear equation represents a line, is represented geometrically by a line. You can have lines that are disjoint. You can have lines that intersect at one point, and you can have 2 lines that are exactly the same that intersect at infinitely many points, right? So 0, 1, infinity. Okay, but for a consistent linear system, it has already a solution. It cannot have 0 solutions. So the only 2 possibilities for a homogeneous system is that either 1, the system has only the trivial solution, right? If it has exactly one solution and it has to have the trivial solution, then it's exactly one solution is the trivial solution. All the variables are assigned 0, or the system has infinitely many solutions in addition to the trivial solution. Okay, so every homogeneous system has to have the trivial solution, right? As a linear system, it has to have either exactly 0, 1, or infinitely many solutions. So it can't have 0 solutions. If it has 1, then it has only the trivial solution. If it's infinitely many, it has infinitely many solutions in addition to the trivial solution. So you have these 2 possibilities for a homogeneous linear system. Is there a question? Okay, no. Okay. So there are no. Okay, I answered all the questions. Okay, so okay, so let's go to the whiteboard for a second. Okay, so I think I mentioned. Okay, let's go here. Okay, so when dealing with homogeneous linear systems of 2 equations, right? So homogeneous linear system of 2 equations, when you look at the graphs of the lines in the linear system, if you had only the trivial solution, then that would mean you would have 2 lines that intersect at the origin. So the intersection point would be at the origin, right? And so this would be only the trivial solution. Okay, so if you have 2 equations, if you had a linear system with only 2 equations and 2 unknowns, and there is exactly one solution, only trivial solution, geometrically you have 2 lines that intersect at the origin, in XY space. Okay, here we're dealing with 2 equations, 2 linear equations. Two unknowns. Okay, so linear system, 2 equations, 2 unknowns, and so the intersection point is exactly one point at the origin, corresponding to the trivial solution. And then the only other possibility for the intersection of 2 equations and 2 unknowns is there's infinitely many solutions. Now you have to have the trivial solution. And so you have a line going through the origin, but then you'd have the same exact line. Okay, so the two equations would have to be represented geometrically by the same line through the origin. And so that's how you have infinitely many solutions. And so the solutions are all the points on both lines that are the same geometrically. So these are infinitely many solutions. And again, this is still for two equations, two unknowns. Two equations in a linear system, two linear equations, and two unknowns. Okay, each equation would be represented by a line to the origin, and in order to have infinitely many solutions, it'd have to be the exact same line. Okay, so an example could be like 2x, x1 plus x2 is equal, that's not this example. Okay, x1 minus x2 is equal to 0. That would be one example. X1 minus x2 is equal to 0. And let's say another one would be 2x1 minus 2x2 is equal to 0. Geometrically, both of those lines are this line, y equals x, pretty much. X1 equals x2, right? Oh, we're using x and y, so I'm going to have to use x and y here. Okay, so you have equals 0, equals 0. So you have x minus y equals 0, 2x minus 2y equals 0. So now you have two equations, two unknowns, and x minus y equals 0 is represented by y equals x. 2x minus 2y equals 0 is also represented by y equals x, or 2x equals 2y, right? Because they're both the same line, and the intersection is infinitely many points, and so they're infinitely many solutions. And then here, this is one example. There's lots of examples. You could have x minus y is equal to 0, and the other one is x plus y is equal to 0. So x minus y equals 0 and x plus y equals 0 has exactly one solution at the origin. Okay, and so that's an example of exactly one solution, trivial solution, or in this example, infinitely many solutions, every point on the same line. Two. Okay. So those are the possibilities, those two. Okay, this is depicted on the whiteboard. Okay, so there is one case in which a homogeneous system is assured of having non-trivial solutions. Namely, whenever the system involves more unknowns than equations. To see why, consider the following example. 4 equations in 6 unknowns. Okay, so there's one case in which a homogeneous system is assured of having non-trivial solutions. Namely, whenever the system involves more unknowns than equations. To see why, consider the following example of 4 equations and 6 unknowns. So this is going to be done on the whiteboard. So this example is going to be done on the whiteboard. Okay, so let's go to the whiteboard. Okay, so our example is the following. Use Gauss-Jordan elimination to solve the homogeneous linear system. So your linear system is x1 plus 3x2 minus 2x3 plus x5 is equal to 0. 2x1 plus 6x2 minus 5x3 minus 2x4 plus 4x5 minus 3x6 is equal to 0. 5x3 plus 10x4 plus 15x6 is equal to 0. 2x1 plus 6x2 plus 8x4 plus 4x5 plus 18x6 is equal to 0. Okay, so we have this, we want to use Gauss-Jordan elimination to solve the homogeneous linear system. It's homogeneous, right? So we have here that homogeneous. It's homogeneous because all of these constants are 0 at the right-hand side, right? And it's a linear system because all the equations are linear, right? So all of these equations are linear. So we have a linear, homogeneous linear system. Okay. We use Gauss-Jordan elimination to solve it. Okay, so if we look at the corresponding, so I'm going to write this here. Let's first write down the corresponding augmented matrix for this linear system. Okay, so I'm going to do that on the next. Okay, so on the next slide, we're going to do that. So I'm just going to write down the corresponding linear system. Corresponding augmented matrix for that linear system. Every time I say that, it's like a mouthful. Corresponding linear system for corresponding augmented matrix for that linear system. So you have 1, 3, -2, 0, 2, 0, 0. And so you have the next row. 2, 6, -5, -2, 4, -3, 0. 0, 0, 5, 10, 0, 15, 0. And the last row is 2, 6, 0, 8, 4, 18, and 0. Okay, so this is the corresponding augmented matrix. So if we look at the earlier example we just did, so if you look at this matrix, and then earlier we had this one. So what's happening is that to the left of this vertical line is the exact same matrix. Okay, so on the left-hand side, we have everything exactly the same. Before we had different numbers here that were not all 0. We had this is not a homogeneous linear system. The left-hand side is the same as this one. Okay, so this linear system now, the left-hand side is the same as in example 5 that we just did. Let me just check something. So this example, okay, so the left-hand side is exactly the same as that of our previous example done on the whiteboard. Okay, so the solution set for this linear system is the same as that of, oh wait, so let me put it another way. When we get this matrix to reduced row echelon form. It's abbreviated by RREF, reduced row echelon form. When we get this matrix to reduced row echelon form, the result is the same as the reduced row echelon form matrix in the previous example, except the rightmost numbers are all 0. Okay, so earlier we started with this linear system. We had this augmented matrix, and the left-hand side is the same. We got this matrix to reduce row echelon form, and we had this matrix. This matrix is in reduced row echelon form, and I'm going to actually write that here. But this matrix is in reduced row echelon form, right? And so this is the matrix, except we had a 1/3 here. These were not all zeros. That matrix, because the left-hand side started out the same, that matrix in reduced row echelon form will be the same as this, except this 1/3 will be a 0. All these will be 0. Okay, so I'm going to rewrite this matrix, except have all zeros on the right-hand side here, and that will be the result of getting this matrix to reduce row echelon form. Okay, and so that matrix, if I can fit it, you know, I'm doing the next page. So so then on the next page, I'm just going to write the reduced row echelon form of this matrix, and it's going to be the same as that example, except with all zeros on the right-hand side. So here's so you have 1, 3, 0, 4, 2, 0, and then a 0. You have 0, 0, 1, 2, and then 0, 0, and a 0 here. You have 5 zeros, 1, 0, 1, 2, 3, 4, 5, 1, and then a 0, and then you have all zeros here. Okay, so now this is the result in reduced row echelon form of that matrix. Okay, and so now that we have this in reduced row echelon form, we're going to want to look at the corresponding linear system. And so the corresponding linear system is, and so the corresponding linear system is x1 plus 3x2 plus 4x4 is equal to 0. Oh. Plus 2x5 is equal to 0. X3 plus 2x4 is equal to 0. And x6 is equal to 0. Okay, and the other one is 0 equals 0, which doesn't matter, and we can exclude it because it doesn't change the solution set at all. Every assignment of variables satisfies 0 equals 0, and so it doesn't reduce our solution set at all. Okay, so it doesn't change it by having it there or removing it. Okay, so now we look at the system, and so now we're just going to find the parametric equations that express all the solutions of this linear system. Okay, so now we find parametric equations that represent all the solutions of that linear system. Okay, to do that, first we locate all the leading variables, which correspond with the leading ones from the matrix. Then we see that all other variables are free variables. Then we assign each free variable its own distinct parameter. Then we solve for each leading variable in terms of the free variables and substitute each free variable for the parameter assigned to it. The result are the parametric equations that we wanted. Okay, so that's a summation of what I'm going to do now. So let's locate the leading variables. Okay, so the leading variables correspond with the leading ones. This is a leading one, that's a leading variable. This is a leading one, this is a leading variable. This is a leading one, that's a leading variable. Okay, all the other variables are now free variables. So that's a free variable. This is a free variable. So these are still free variables, right? So these are all free variables. Maybe I'll just circle each of the free variables once instead of every time it appears. So, okay, so those three are free variables. And so, okay. So then those are the free variables. I'm circling x4 twice. It's only one variable, but all those are free variables. And then, so we're going to solve for each leading variable in terms of the free variables. And then, right. Okay, so the free variables are x2, x4, and x5. Those are our free variables. And so each of them is going to be assigned its own distinct parameter. This equals r, s, and t. And so then we're just going to express each of the leading variables in terms of the free ones. And so x1 is equal to negative 3x2 minus 4x5 minus 2x5. So this is going to equal negative 2, that. Negative 3 x2. I'm just going to use the colors so that way you can see. This is the x2 still. This is minus 4 x4. And then minus 2 x5. X3, which is another leading variable, is equal to, I'm just going to use the black for the equal sign. X3 is equal to negative 2 x4. And then x6, which is the other free variable, the other leading variable, is equal to 0. Okay, so the free variables we reassign parameters are s and t. You can see that here in the pink. And then the free variables, which are blue, we set them equal to those expressions from earlier. And then we substitute each of those free variables for the corresponding parameters. And so you get that equals to negative 3r minus 4s and minus 2t. This is equal to negative 2 x4 is s, and it still equals 0. So x1 is equal to negative 3r minus 4s minus 2t. x3 is equal to negative 2s. x6 equals 0. And so the result of all this is that we get our final parametric equations describing all the solutions of this linear system. And it's x1 is equal to negative 3r minus 4s minus 2t. x2 is equal to r. x3 is equal to negative 2s. That's a t. X4 is equal to s, and x5 is equal to t, and x6 is equal to 0. Yeah, that's a 0. Okay, good. So there we go. Okay, so those are the parametric equations describing all solutions of the original linear system. Okay, and so those are parametric equations describing all the solutions of the original linear system. Okay, and when r equals s equals t equals 0, when you assign all the parameters equal to 0, you get the trivial solution. You get x1 equals 0, x2 equals 0, x3 equals 0, x4 equals 0, x5 equals 0, and x equals 0. Okay, and so just note that the trivial solution results when r equals s equals t equals 0. Okay. Okay. So this last example illustrates two important points about homogeneous linear system, about solving homogeneous linear systems. Okay, so I'm going to actually move to the whiteboard now. Okay, so let's go to the whiteboard. Okay, so I'm just going to write this again. This example illustrates two important points about solving homogeneous linear systems. The first thing is that elementary row operations do not alter the columns of zeros in a matrix. So the reduced row echelon form of the augmented matrix for a homogeneous linear system has a final column of zeros. Okay, this implies that the linear system corresponding to the reduced row echelon form is homogeneous, just like the original system. Okay, so elementary row operations do not alter the columns of zeros in a matrix. So the reduced row echelon form of the augmented matrix for a homogeneous linear system has a final column of zeros. This implies that the linear system corresponding to the reduced row echelon form is homogeneous, just like the original system, right? So if you start with homogeneous linear system and you look at its augmented matrix, the rightmost column is all zeros. And if you get that to reduced row echelon form, you'll still have a matrix with all zeros. The rightmost column of all zeros, and its corresponding linear system will have to be homogeneous because all the constants on the right-hand side will have to be 0. Okay, 2. When we constructed a homogeneous linear system corresponding to the augmented matrix, we ignored the row of zeros because the corresponding equation, which was 0x1 plus 0x2 plus 0x3 plus 0x4 plus 0x5 plus 0x6 is equal to 0. Does not impose any conditions on the unknowns. Thus, depending on whether or not the reduced echelon form of the augmented matrix for a homogeneous linear system has any rows of zeros, any rows of zeros, any rows of zero. Save, okay. The linear system corresponding to that reduced row echelon form will either have the same number of equations as the original system, or it will have fewer. Okay, so when we constructed the homogeneous linear system corresponding to the Augmented Matrix, we ignored the row of zeros because the corresponding equation, this one, does not impose any conditions on the unknowns, 0 equals 0. Thus, depending on whether or not the reduced echelon form of the Augmented Matrix for a homogeneous linear system has any rows of 0, the linear system corresponding to that reduced echelon form will either have the same number of equations as the original system, or it will have fewer. Okay, so if you have a homogeneous linear system, you have its corresponding augmented matrix, you get it to reduced echelon form. Either the linear system corresponding to that matrix in reduced echelon form either will have the same number of equations as the original system, or it will have fewer. It will not have more. So have the same number or fewer, because you may have equations that end up being 0 equals 0, which you can exclude. In that case, you'll end up with fewer equations. If that doesn't happen, you'll have the same number of equations. Okay. Okay, so a new thought. Okay, now consider a general homogeneous linear system with n unknowns in reduced row echelon form with r non-zero rows, and thus n minus r free variables. Okay. Never mind. Okay. Okay. So now consider a general homogeneous linear system with n unknowns in reduced echelon form with r non-zero rows, thus n minus r free variables. Okay. It is of the form. Well, so if you have r non-zero rows and it's in reduced echelon form, that means that every non-zero row has a leading 1, which corresponds with the leading variable. So all of the having r non-zero rows in reduced echelon form matrix means you have r leading variables. So if you have r leading variables and there's a total of n equations in n unknowns, that means if you have n unknowns and exactly r of them are leading variables, that means the rest of them are free variables. There's a total of n variables and r of them are leading variables, and so there are n minus r free variables. The total number of variables minus the number of leading variables is the number of free variables, n minus r free variables. And so this general homogeneous linear system with n unknowns in reduced echelon form with r non-zero rows and thus n minus r free variables is of the form of the following form. X sub k sub 1 plus sigma of parentheses. I'll explain what that notation means. And the next one is x sub k sub 2 plus sigma of that, which equals 0. The next one is x sub k sub 3 plus sigma parentheses equals 0. And then you continue this process, dot, 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 and then it continues to x sub k sub r plus sigma parentheses equals 0, where in each equation, the expression sigma blank denotes a sum that involves the free variables, if any. Okay, so so what's happening is we have R leading variables corresponding to those R non-zero. So we have R leading variables, and so we have K1, K2, K3 up to including KR. The reason why it's not 1 to R, the reason why it's not X1, X2, X3, XR, it can't be because we only know there are R leading variables. We don't know which of the variables are leading variables. We only know that there are R of them. So let's say you had X1, X2, X3, X4, X5, X6, X7, X8, X9, and X10, and you only knew 3 of them were leading variables. Well, you couldn't say X1, X2, X3 are leading variables. Instead, you would develop the notation that says 3 of them are. And so you'd have an index K1, K2, and K3, where K1 is the first leading variable, K1 is the first index of the leading variable, K2 is the second index of the leading variable, and K3 is the third index of the leading variable. So if you had X1, X10, and X2, X4, and X6 were leading variables, then that would mean that K1 equals 2, K2 is equal to 4, and K3 is equal to 6. And so the Ks in order are in order the indices of the leading variables. And since there are R leading variables assumed, that means you have K1, K2 through KR indices that correspondingly are the R indices for the R leading variables. Does that make sense? So you have XK1, XK2, XK3 up to including XKR, and those are the R leading variables. And the Ks, K1 to KR, are the indices of those R leading variables of the total N variables. Okay, but then every time you have a leading variable, then what you have is plus an expression of only free variables. So plus the sigma of, in parentheses, plus this means this is an expression involving only free variables. This is also an expression of only free variables. So is this, and so is this. It's not the same expression for each equation. Each equation has its own expression involving only free variables. And so what we're just saying is that if you have N, you have R leading variables, correspondingly N minus R free variables, and each equation is its own distinct leading variable, one of the total R of them with the right notation, and then adding an expression of only free variables to equal 0. Okay, and so in this way, you have a system of this form. Okay, so you have a general homogeneous linear system with N unknowns in reduced row echelon form with R non-zero rows and this N minus R free variables, and it has this form. Okay, and these again mean expressions involving only free variables in the system. Okay. Okay. If a homogeneous linear system has N unknowns, and if the reduced row echelon form of its augmented matrix has R non-zero rows, then the system has N minus R free variables. Okay, so if a homogeneous linear system has n unknowns, and if the reduced rational form of its augmented matrix has r non-zero rows, and the system has n minus r free variables, I already said that. Okay, so that's a fact. Okay, I'll write the fact here. Okay, so here's another theorem. We're almost done, just a few more minutes. Theorem 1.2.2, a homogeneous linear system with more unknowns than equations has infinitely many solutions. Okay, once you have a homogeneous linear system with more unknowns than equations, what that means is that the number of leading variables is at most the number of equations. Each equation can have at most one leading variable, right, corresponding to a leading one in its augmented matrix. So every equation can have only at most one leading variable. That means that if you have more unknowns than equations, then that means if you were to have 10 equations and there can only be at most one leading variable in each equation, if you had 5 equations and 10 unknowns, the most number of leading variables you could have is 5. That would mean you would have free variables, right? So once you have a homogeneous linear system with more unknowns than equations, it has to have at least one free variable. And a free variable is assigned a parameter in the parametric equations. And so once you have a parameter in the parametric equations representing the solution set of a linear system, a parameter can be assigned any real number. And each real number it's assigned to gives its own distinct solution of the linear system. And so having at least one parameter means for that parameter and every parameter, you can assign infinitely many values to it and get a distinct solution. That means you have infinitely many solutions. So once a homogeneous linear system has more unknowns than equations, you know it has at least one free variable, which corresponds to a parameter assigned to it, which can be given infinitely many values, each having its own solution, each corresponding with a distinct solution of the linear system. And so you have to have infinitely many solutions in that case. Okay, see an example of what? Erkan? Example of what? A linear system.
Yeah, I meant of like the x k1, x k2, x k3.
Okay, so I was saying it out loud, right? How if the indices, it takes a while to write these things down. I can explain to you. I don't know if it's a point, if you're having trouble with it, I guess. If more unknowns than equations, right here, this example. See how many unknowns are there in this system?
3 or 6.
No, unknowns. Variables. How many different variables are there? Tell me what the variables are in that system.
Like of the free variables?
Any variable. X1, what's another one?
Oh, x2, x3, x4, x5, x6.
Right, so how many variables are there? How many unknowns are there?
6.
Good. How many equations are there, excluding the last one?
3.
Good. So there are more unknowns than equations, right?
Oh, okay.
How many leading variables are there?
3.
Right. How many free variables are there?
3.
Good. There's at least one free variable, right?
Yes.
Okay, so now since there's at least one free variable, we have at least one parameter, right?
Okay.
And now when we get the parametric equations describing the solution set of the linear system, since we have at least one parameter, we can assign all the parameters infinitely many values. So that parameter corresponds with infinitely many choices, each choice giving its own distinct solution. That means we have infinitely many solutions. Does that make sense?
Okay, I got it now. Thank you.
Okay, good.
Thank you.
Sometimes the best way is to see an example, and actually sometimes it's just best to see the situation without looking. Like in that case, I think it would be better not to look at a specific example, kind of, but just see the example. Well, I guess we do. Okay, anyway. Okay, so class ends at 9:50, right? So we're done. Okay, so let's stop here. This is a good place to stop. And next time we'll continue and finish to the section we're on, which is 1.2. Okay, these early sections are very long. Okay, so we don't have class on Thursday because we have a holiday. It's Rosh Hashanah, so the school's closed. So our next class is next Tuesday. So I'll see all of you next week on Tuesday.
Professor, did you got my name on attendance?
So I took attendance. Attendance is due today, and I already handed it in. But I think I got you because I handed it in. I think I had perfect attendance on it. Yeah, this is Ahmed Hassan.
Yeah.
Yep, I got you. I have a check next to you. You told me
Fine.
last time you were here.
All right, thank you.
No problem. Okay, so everyone was marked present. Nobody was marked absent. So you're all good. Okay, so I'll see you next Tuesday. Good night.